For this question, what we want to do is to determine the values of alpha such that the limit as t approaches infinity of yt is 0. So the first thing we can do is just solve this second order differential equation. And what we would do first for that is to convert this into a system of first orders. The way we set that up is we have x1 equals y and x2 is equal to y prime. So our first equation would be x1 prime is equal to x2. And then for our second equation, we plug in our values for x1 and x2 into our original differential equation. We can rewrite this second equation to look like this. Note that we can rewrite the second term to look like this. So now if we convert these two equations into matrix form, what we get is now we can try and solve this equation. This is our matrix A, and we want to solve this equation using the eigenvalue method, where we have our solution where v1 and v2 are eigenvectors and lambda1 and lambda2 are eigenvalues. So now to solve for eigenvectors and eigenvalues, what we want to do is solve and rewriting this, we get which we can write in quadratic form like so. Solving this using the quadratic formula, we can find our two eigenvalues. We can see here that a lot of the terms inside the square root cancel out, and we're left with this as our values for our eigenvalues. So these are our two eigenvalues. Now we can find the eigenvectors. We have our eigenvector here to be similarly for the second eigenvalue of alpha minus 3, so now that we have our two eigenvalues and eigenvectors, we can write our solution for our system in X as but the solution we found so far is just our solution for our system in X, where this is equal to x1 and x2. But the question gave us a differential equation in y, so our solution should also be in terms of y. And we want to find the values of alpha such that yt approaches 0. As we see here, we set x1 to be y, and then we set x2 to be y prime. So plugging that in here, we get x1 is y and x2 is y prime. So since we want our solution in just y, we look at the first row of our solution, and we get And just a side note before we move ahead here, if we take the derivative of our yt, we should get our second row here, and we see that we do. A derivative of c1 e to the alpha t would be c1 e to the alpha t times alpha, which is what we have here. And then c2 e to the alpha minus 3t would be c2 e to the alpha minus 3t times alpha minus 3, which we have here. Okay, so now that we have our general solution in y, we want to find the values of alpha such that this limit approaches 0. So we want, well, taking the limit here, we can see that we can write this as the sum of the limits of the two terms. We have and we want both of these to be equal to 0. So what that means is we have the limit as t approaches infinity of e to the something t. Well, this approaches 0 if k is less than 0. And then it approaches infinity if k is greater than 0. And if we want this to be equal to 0, we want to have both alpha and alpha minus 3 have to be less than 0. So what that means is we want both of the exponents for our exponentials to be negative. So we have alpha should be less than 0, and alpha minus 3 should be less than 0. So this right one just means alpha should be less than 3. So then our final solution is alpha less than 0. So what are the values of alpha such that all solutions tend to 0? So no matter what our values for C are, right, it could be a positive, negative, or 0. As long as our alpha values are less than 0, then the limit of all our solutions will be 0 as t approaches infinity.